example 6 that we apply the material balance that you study with the principle of chemical engineering. I think it's the same example. I review about the material balance for the crystallization processes. For this example, we have an aqueous potassium nitrate. Aqueous potassium nitrate. This is, we would like to crystallize potassium nitrate from the solution. The phase is the solution with the liquid phase. In the liquid phase contain 50% potassium nitrate, 50% potassium nitrate, and the balance is 40% is water. At 80 Celsius, we do the cooling crystallizer. That's like cooling crystallizer. For this case, we cool the temperature at constant concentration until it leaves the supersaturation for crystallization. Okay, this cool to 40 Celsius, from 80 to 40 Celsius. Okay, for this case, determine the temperature at which the solution is saturation. Calculate the temperature of the saturation. And the percentage of potassium nitrate in the feed that's formed in crystal. For this case, this means calculate the percent of crystal that's obtained from the feed. Okay, from this case, we can draw the diagram. We have one unit operation. Right, we have one crystallizer, and we have feed. Feed contains 60% potassium nitrate and 40% water. It's 0.6 kilogram of potassium nitrate per kilogram total and 0.4. In this case, a liquid phase. Liquid phase at 80 Celsius. Liquid phase. Okay, for this case, we use the basis is 100 kilogram of feed. 100 kilogram of feed at the basis of calculation. Okay, and the output we have two products. We have the solution or liquid and solid. So we have two, liquid and solid. Liquid is also saturated solution. Saturated solution at 40 Celsius. And also the saturated, how many amount of saturated solution is M1. That's like M1 means amount of the saturated solution, and X is the fraction of potassium nitrate in the solution. That's right. X is the fraction or the concentration of potassium nitrate in solution. M2 is only the crystal. This is only potassium nitrate. That's right. This is only one component. These two components, potassium nitrate and water. This potassium nitrate and water. There are two components. These two components. These two components. This is only one. Two, one. That's right. Two, one. But this is the liquid phase. This is the liquid phase. This is the solid phase. That's right. We have two phase system. Okay. This is the condition. Okay. And then for this case, we can convert solute per solvent ratio. For this case, we have to determine the saturation. Right. From this curve, this is the solubility curve. Okay, for this case, we feed 60 grams of potassium nitrate per 40 grams. That's right, the total is 100. Multiply 0.6, you get 60 kilograms of potassium nitrate per 40 kilograms or 40 grams of water. That's right, water is the same ratio. Kilogram or gram is the same ratio because this is also gram, this is also gram or kilogram or kilogram. The ratio is the same. Don't worry about it. You get 1.5 gram potassium nitrate per gram water, or equal to 150 gram potassium nitrate per 100 gram of water. This is the feed ratio. Okay, the feed ratio. And then you have to calculate what is the saturation temperature of this concentration. That's right, of this concentration. Okay, we'll use this curve. This is for potassium nitrate. This curve for potassium nitrate. The concentration for this case is 150 per 100 gram water. This is solubility in unit of gram per 100 gram of water. For this case, is 150. At this point, you get about That's right. This is 74 Celsius. That's right. The concentration that we feed at ST. This is the feed temperature at 80 degrees Celsius. We feed temperature at 80, but 80 is not saturated. 80 is undersat. That's right. This is undersat zone. Okay. This is the undersat zone. At 80 is the undersat. This feed point at 80. And then we reduce the temperature until cross this point. This is the saturation temperature at this concentration. And then you reduce the temperature more to 40. That's right, to 40. This is supersat, which can crystallize. That's right. How many crystal can be obtained? It can be different like this. At 40, this is the saturation at 40. This is saturation at 74. And then it's a driving force or the difference of concentration. You can calculate amount of crystal that crystallize from this point and this point. Okay, from the first question, one is the saturation temperature of this concentration of the feed concentration is 47 at 74 Celsius. That means we feed at 80 and the saturation is 74 Celsius. Okay. That means we feed at undersat. We feed at 85 undersat. And then we reduce the temperature to 74. You get the saturation. And then you reduce the temperature further. You get super saturation. And then you can induce the crystalline. Okay, now you know the saturation temperature of the feed. And then you can take the balance. We have three components. M1X, M2 is unknown. That's right. M1X, M2 is unknown. And also we have three unknown and two independent balance. And we have one information about the solubility. You get 0 degree of freedom. You get 0 degree of freedom. Why we know the solubility? Because you know the temperature. The output temperature is 40. At 40, you can calculate the composition at saturation. 40 Celsius, okay. You know this is the concentration or the ratio of potassium nitrate per water. That's right, per water is about 63. That's right, about 63. This is 63 grams of potassium nitrate per gram of water. Per 100 grams of water. That's right, at this point. Okay, from this point, this is the X. That's right, X is the kilogram potassium nitrate per kilogram water. Okay, now you know at this point. That's right, 60 grams potassium nitrate per 100 grams water. Okay, we can put that it's 63 kilograms potassium nitrate per 60 kilograms potassium nitrate plus 100 kilogram water. That's I did the and you can get the fraction. This is the fraction of potassium nitrate. This is X. Now we have three unknown. -2, -1, you get 0 degree of freedom. Okay. You can balance because you reduce the unknown by X. Okay, now you have M1 and M2. You can apply the balance for water or total mass balance or potassium nitrate balance. We have three choices. That's right. We have only two equations. That's right. Okay. We need only two. For this case, we balance on water balance and total mass. You can balance on water and potassium nitrate, or you can balance on water and total mass. You can balance on total mass and potassium nitrate. We have three choices that is possible. Okay. For the example, we choose two balance: water balance and total mass balance. Water balance, for this case, we balance based on steady state, flow in, flow out continuously. That's right, no reaction, no gen, no con, no accumulation. Right, input equal to output. How about the water input? Water input is 0.4 multiplied 100. That's right, 0.4 multiplied 100. We have two output. Two output, 1 minus X multiply M1. That's right, it's water. Because X is potassium nitrate. And there is no water here. Okay, we have only one input and one output. Right. Get like this. X you can solve for M1. Okay. And then you can balance on potassium nitrate balance or total mass balance. For this case, we total nitrate. That's right, total mass balance. 100 equal to M1 plus M2. M1, you can solve for M2. Okay, this is for the example for the mass balance applied for the crystallization process. That's right. And also the percent of crystal, that's right, percent obtained from the feed. For this case, we got M2. M2 is pure crystal. That's right. Only potassium nitrate is 34.9 kilogram potassium nitrate. But how amount of the potassium nitrate in the feed? In the feed, we have 0.6 multiplied 100 equal to 60. That's right. This is the amount of potassium nitrate in the feed. Then you can calculate the percentage of potassium nitrate crystallized. The crystallized is 34.9 divided by total multiplied by 100, you get 58.2%. This is the percent of the potassium nitrate that crystallized from the solution. Okay. For this case, if you would like to balance for the crystallization process, you have to know the solubility data. You have to know this. Right. You have to know this information. It's very important. That's right. It's very important to know. Okay. Right. For the next example, we talk about the crystallization, but we talk about the anhydrous and hydrate. Right. Anhydrous and anhydrate. I think you study in chemistry. I think you know it's when solid or crystal form, it's maybe some molecule of water. That's right, molecule of water also interact with the molecule of solid. For that case, we call hydrate crystal. Hydrate crystal means the crystal obtained and also mixed with the water molecule. This is interact in the crystal structure or in the lattice structure. That's right, in the lattice structure. Like for example, anhydrous means no water or water-free crystal. Magnesium sulfate, there is no water. That's right, there is no water. Obtain this at higher 100 Celsius, right? And magnesium sulfate monohydrate. Monohydrate means mono means one. That's right. It's one water, one molecule of water. Hexahydrate, 6 molecules of water. Heptahydrate is 7 molecules of water. Dodecahydrate, that's right, this is the 12 molecules of water. We call this is the hydrate. Hydrate means the crystal incorporate the water more in the crystal. That's right, more in the crystal. And this is the condition to obtain this crystal. That's right. If you would like to obtain anhydrous magnesium sulfate, you should be crystallized at the temperature is higher than 100 Celsius, for example. That's right. Okay. This is the hydrate and anhydrous system. Okay. For this example, right, an aqueous solution magnesium sulfate at 104 Celsius. This is including 30.1 ton or 30.1% of magnesium sulfate, and balance is water. That's right. 30.1% of magnesium sulfate, 69.9% is water. This is the meaning of this. Okay, for this we use cooling crystallization also. That's right. We operate at 10 Celsius. We cool from 104 to 10 Celsius. And the stream leaving the crystallizer is slurry. Slurry means solution and solid mixed together. That's right. Okay, for this case, solid magnesium heptahydrate. That means the crystal that we obtain is magnesium sulfate. That's right. Magnesium sulfate includes 7 molecules of water. 7 molecules of water. Okay. Okay, and also for this case, show determine the rate at which solution must be fixed to the crystallizer to produce 1 metric ton or 1,000 kilograms. For this case, we would like to produce 1 1,000 kilogram or 1 ton of magnesium sulfate heptahydrate per hour. This is the production rate. The site production rate is 1 ton or 1,000 kilogram of magnesium sulfate heptahydrate. We would like to produce the magnesium heptahydrate. That's right, magnesium sulfate heptahydrate. Okay, this is the production. Okay, what is the unknown? That for this case we utilize M1. M1 is the flow rate of the feed. That's right, for the feed. For the feed, we know fraction and output. We have two components. We have solid. Solid we know because we would like to get 1,000 kilogram. This is no. And liquid or solution, we represent by M2. M2 is the liquid solution. The liquid solution is also at saturation system. This contains magnesium sulfate and water. That's like magnesium sulfate dissolved in water. How to determine the fraction of magnesium sulfate and water at the outlet? For the case, you know temperature. That's right, you know temperature. In the same period, you have to determine the solubility at 10 Celsius. But for this case, we obtain the solubility from textbook like this. We know right at 10 Celsius, we know 23.2% weight magnesium sulfate. That's right. We know the saturation or solubility of magnesium sulfate in water. That's right. This is magnesium sulfate, not magnesium sulfate hydrate. That's right. This is a hydrate. That's right. It's hydrate. Okay, it's about 23.2 magnesium sulfate and 76.8 is water. This is the solubility. That's right. Solubility. Okay, and M2. Okay, for this case, you draw already. That's right. This the flow chart. We know input, we know output. We have only two components. That's right. Two components and two unknown. You can solve this data. That's right. You can solve this data. Okay, you can solve by the total mass balance or magnesium sulfate balance, total mass balance or water balance and magnesium sulfate balance. Okay, for this case, we balance two. That's right. Total mass balance and magnesium sulfate balance. How about the total mass balance? M1 equal to 1 plus M2. That's right. We have M1 equal to 1 plus M2. This is two unknown. That's right. We have equation 1. And equation 2, you use the magnesium sulfate balance. Magnesium sulfate. For magnesium sulfate balance, the inlet is 0.301 multiplied M1. This is the magnesium sulfate inlet. Magnesium sulfate outlet, we have two components. That's right. We have two components in the solid form and in the liquid form. In the liquid form is 0.232 multiplied M2. This is inlet. Right. This is outlet in solution form. M2 is ton of solution per hour multiplied 0.232 ton magnesium sulfate per ton solution. This is inlet. This is This is inlet. This is outlet in liquid form. In liquid. And this is outlet in solid form. But in solid form, it is in terms of hydrate. That's right. It's hydrate. Okay. We balance magnesium sulfate, not balance magnesium sulfate heptahydrate. Okay. For this case, you have to calculate the molecular weight of magnesium sulfate heptahydrate and magnesium sulfate. Okay, for this case, you know the outlet is 1 ton per hour of magnesium sulfate hydrate. And you also know like the molecular weight of the magnesium sulfate heptahydrate. It is 246.4 ton per mole. That's right, ton per mole, ton per ton mole. And molecular weight of magnesium sulfate is 120.4 ton per ton mole. That's right. Mole and mole is cancelled. Right, mole and mole cancelled. Okay. For this case, you can calculate like the this is equation 1 and equation 2. You can solve simultaneously equation 1 and equation 2. You get M1 and M2. Okay, this is the application if the system is incorporated anhydrous and anhydrate. Anhydrous and hydrate. That's right, anhydrous system. Okay, these two examples, we talk about the material balance that you study in the PCE, Principle of Chemical Engineering. Okay. And I talk to you, the kinetic that we would like to crystallize the crystal from solution. We have two kinetic, nucleation and growth. That's like nucleation and growth. But if you would like to crystallize, you have to know the basic or the important parameter, right? We call it the solubility, right? Solubility. We have many techniques that use solubility measurement. That's right. The solubility means the maximum amount of solid that can be dissolved. That's right, in the solution or in the liquid. Like for example, if you would like to dissolve sugar in water at 20 Celsius, that's right, at 20 Celsius, there are only maximum amount of the sugar that can be dissolved at 20 Celsius. If you add more and more crystal at higher than solubility, the solid sugar cannot be dissolved. That's right, cannot be dissolved. And also, if amount of the sugar is less than solubility, if you add more, okay, it's dissolved until it reaches the solubility. This is the solubility, that's right, solubility definition. There are many techniques. The technique that I use the gravimetric method at isothermal condition. That's right, at isothermal condition. The isothermal means at constant temperature. We fix temperature. For example, we have the reactor or we have the catalyzer. That's right, we control the temperature using the water bath. That's right. This is the water bath. And then you control temperature at, for example, at 25 Celsius. Okay, 25 Celsius. Right. And also we have a mixer impeller to mix, to induce the crystal dissolve or the solid dissolve. Like that. And then we have the water cut solid in excess. We add more and more solid inside the reactor. And we know the amount of water, we know amount of solid. Right. And then you mix together. It's maybe when you start to mix it, you take the sample. That's right. In the system, we have liquid and solid. That's right. We have liquid and solid. In liquid, we have two components: solid that dissolve in liquid and water. That's right. We have two components for that case. The solid is only one component. That's right. Solid phase is one component, but liquid phase we have two components. Okay. When you sampling, that's right, we have solid sample and liquid sample. We sampling with the filter. That's right. You filter the solution. We only collect the liquid solution or the clear liquid to determine the concentration. And then the technique for this case, you can plot the time and concentration. At time 0, there is no solid dissolved in liquid. This maybe start from it. When time proceeds, you can get like the concentration is increased and then constant. That's right. And then constant. What does it mean? The constant means the solubility. That's right. Because the solid cannot dissolve further. Because it's reached the solubility already. It's the maximum. That's right. It's maximum. You get, and then you can measure the solubility at the maximum concentration or at the constant concentration. Because the concentration cannot increase because it's reached the solubility. It reached the equilibrium already. This is the technique of the gravimetric method. That's right, gravimetric method. And the second technique, we use like the polythermal method. The gravimetric with isothermal, constant temperature, but polythermal means temperature is varying. That's right, temperature is varying. For this case, we fix concentration. That means you prepare the concentration that you know amount of liquid, you know amount of solid, you know amount of liquid, you know amount of solid, and then you stir or mix, that's right, and also heat. For this case, you measure the temperature and write the turbidity, turbid, that's right. For this case, we check the temperature and turbid. Like we initially with the solid and liquid. The point of the turbidity is the point of the clear point. When all of solid dissolve to the solution, that's right, you record the temperature at that point. You mean at that point the temperature is saturated, that's right, saturated. And also for this technique, you can obtain the temperature with correlate with the concentration, that's right, concentration. For this technique, you determine the concentration that change with time until it is the constant. This is the equilibrium or the saturated or solubility. But for this technique, you prepare the concentration. You know the concentration at initially. That's right, because you know amount of water, you know amount of solid. And then you heat up for the solid. That's right, you record temperature, you record the turbid. That's right. When the solid is dissolved to the liquid or of solid dissolved to the liquid, from the turbid solution, it will be clear solution. That's right, you will clear solution. The point that the turbid solution change to the clear solution, we call that the saturation point. And also the corresponding temperature is the saturation temperature. This is the technique that we will use in my lab, two techniques. Okay, we can measure the FBIM to the turbidity. Like we have the count is the number of crystal. And also this is the time. And this is the temperature. This is the temperature. Right. This is the number of crystal. The number of crystal is increased until it reduced to the minimum. That's right. This is the number of crystal is 0. What does it mean? Number of crystal is 0. There's no crystal. It dissolves to the solution. And this is the temperature. Right. At this point, we call the solubility line at n equal to 0. And temperature at this point is also the solubility. Okay, this is the technique to measure the turbid. We use the FBIM. FBIM, we count the number, that's right, the number of solid. If the number of solid is 0, that means you get the clear point of solution. Okay, this is the technique to determine the solubility. Okay, for the beginning of the crystallization, I think you have to know the term of solubility, that's right. And also we have important kinetic nucleation and growth. The nucleation we start from the solution, that's right. It may be solution, a molecule, it's random. And then when you induce the temperature by reduce temperature or evaporation or add some additive to reduce the crystallization. Molecule of the solute, that's right, go together. More and more. And then we build the cluster of the molecule. That's right, the cluster of molecule. And the time process, we get the crystal. And then crystallize at solid state. This is the step, but we start from the solution, the clear solution. That's right, the clear solution. When you trouble the condition of the solution by at that pH, at that temperature, at that pressure, that's right, or adding some additive, adding solvent, adding the precipitant, adding the crystallizing agent, something like this. When you trouble the condition of the concentration, the molecule will be moved and then go together until it's big and big in the cluster of the atom or molecule. And finally, we create the crystal or generate the crystal. That's right. This we call the nucleation. Nucleation means generation or the birth of a new crystal. Birth of the new crystal. We have two kinds of the nucleation: is primary and secondary. That's right. The primary, the crystal nucleate from the clear solution. But the secondary nucleation is the nucleation is generated from the seed crystal. We have the seed. And we have some breakage, that's right, from one crystal break into three crystals. It's maybe from the attrition of the crystal. It's maybe from the shear, that's right, shear of the crystal, something like this. This is the secondary nucleation. The secondary nucleation, the nucleation is generated from the whole crystal or the seed crystal. From one crystal, it's break, that's right, from one into two into three crystals, something like this, because the number of crystals is increased. But the primary, the crystal is generated from the clear solution. Right. We have two techniques: homogeneous. This very high concentration, very high concentration. If you operate at very high concentration, the crystal will be generated spontaneously itself. And also, if we have some foreign particle, right, we have some foreign particle to induce the nucleation. It's also nucleate. This is also heterogeneous nucleation. Because in our solution, there are some foreign particles. The foreign particle is not the crystal of the solute, it's different crystal. This is the technique of nucleation. Aside the technique of nucleation. Like for this, we can separate like the metastable zone. This is the metastable zone. This zone is okay for secondary nucleation. Sorry, this is for the metastable zone, right? For the secondary nucleation, but the concentration is higher than this. Mostly is primary and heterogeneous nucleation. As higher concentration, it's also like nucleation by primary or homogeneous. But for the secondary nucleation, for this case, the secondary nucleation, this zone is also superset, but lower concentration than the heterogeneous or homogeneous, because the concentration is quite low and the driving force is quite low. It's difficult to generate the new crystal. For this case, we can generate the crystal by the secondary nucleation. But for this case, we mostly operate for the growth, right? In the metastable zone, we operate like the growth. Right? If you control the mixer, you control the flow rate, you can eliminate the secondary nucleation. That's right. We can eliminate the secondary nucleation if you operate at the optimum condition, like the good mixing, good flow. That's right. And also you can eliminate the secondary nucleation only for growth. Because the growth, we would like to control the size of the crystal. That's right. In the higher concentration, it's difficult to control the size because we also have the new crystal generated and crystal growth together in this zone. Okay, it's difficult to control the size. Okay, if you operate at lower concentration at the metastable zone, okay, we can control the size of crystal. This is more operate in industry application. You would like to control the size of the crystal. I talked to you already for this case. What is the primary nucleation? We separate in homogeneous and heterogeneous. Okay. And also did I show you the equation that can be described the nucleation? That's the most common theory. We talk about the classical nucleation theory. That's like classical nucleation theory. We can estimate the nucleation rate at term of J. J is the nucleation rate. It's a function of the concentration in terms of supersaturation. Supersaturation is C divided by C star. C is the actual concentration divided by the equilibrium or solubility. And also it's a function of parameter A and parameter B. Like this. And parameter B is also in terms of the what is this? Molecular volume. That's right. And also is the gamma is interfacial energy, and also the temperature and both mode constant. That's right. What is the parameter B is a function of the interfacial energy. That's right. Interfacial energy between solute and solvent. That's right. Solute and solvent. For higher interfacial energy, it lower nucleation from this. Higher interfacial energy, lower nucleation. Higher temperature, higher nucleation. These two parameters is very important because it's the temperature and interfacial energy. And again, the higher interfacial energy, it lower nucleation. Why? Because it's higher interfacial energy. We need high energy, that's right, to separate the solute from liquid like that. And also the higher temperature was easy to generate the nucleation or the crystal. This is the basic theory that we apply to describe the nucleation. We call this classical nucleation theory or CNT. That's right, CNT. And also in the point of view, in industrial crop oil view, we can also explain the nucleation based on the power law model. The power law model. It may be burst rate equal to KNC minus C minus C is driving force for crystallization. Power B. That's like Kn and B is the physical property of the system. It may be obtained from the experimental data. That's right. It also depends on temperature, impurity. That's like operating condition is mainly intensity of the aggregation concentration of the crystal in suspension. That's right. The next one we call like the secondary nucleation. The secondary nucleation, as I talked to you previously, we have to operate in the metastable zone. For this case, like this zone is the lower concentration. That's right. It's difficult to try the primary nucleation. If we have some crystal seed in this, okay, it's possible for secondary nucleation. But in industry, we need to avoid the secondary nucleation. That's right. If we have the secondary nucleation, that means we get a lot of crystal and the different inside. That's right. But for this case, you have to control the condition, control the mixing rate, you control the temperature, you control the concentration, like this. You control the seeding rate also. Right. We would like to operate only the growth in this zone. In this zone. Okay. Okay, what is the possible kinetic for the secondary nucleation? It may be the contact nuclei or contact nucleation. The contact between crystal and crystal. We have two crystal contact together. It may be breakage. That's right. Or crystal contact with the vessel. That's right. The vessel wall. The crystal contact the vessel wall is also breakage. Or crystal contact with the impeller. It's also the breakage. That's right. For the breakage. And for this contact, it also maybe from that we have crystal. We have some the solute attached on the surface of crystal at the interstep. This contact, crystal contact, crystal vessel contact, crystal impeller contact, it may be removed and absorbed layer. We can remove this. That's right. If this layer is removed, and also this layer is growing into the crystal, that's right, and increase inside. Also, we get a new crystal from that case. And also, shear nucleation. The mechanism like the same. That's like crystal impeller, crystal vessel wall. But this is the effect of fluid shear. That's right, fluid shear. Fluid shear is remove this surface to be a new crystal. And the third mechanism we call it fracture mechanism, is fracture nucleation. It's based on the breakage of the one. That's right. For this case. Okay. For the magnesium, the contact crystal reservoir, crystal impeller is maybe remove the adsorbent surface to be the new crystal, or it's maybe removed by the fluid shear. And the third step is break it aside from one crystal to be 2, 3, 4 crystals, something like this. And another technique is the attrition nucleation or attrition nuclei. This is the crystal from the larger crystal. Aside from the larger crystal, it's fragment or break it by the technique of attrition. That's right. Attrition for this case is attrition or attrition fragment. That's right. And the last one, some crystal we have like for this crystal, there are some like this crystal. This can be break. That's right. This crystal can be break into one more crystal. This is also the nucleation. Okay, this is the possible find mechanism for the secondary nucleation. Again, the nucleation means the new crystal form. That's right, new crystal form. For primary nucleation, the crystal form a clear solution. For secondary nucleation, the crystal or number of crystals increase based on the mechanism of breakage or shear nucleation or contact nuclei or attrition nuclei or needed breathing, something like this. We have from one crystal break into 2 crystals, or from one crystal the adsorbent surface is removed by the shear, it removed by the contact. We will get one more crystal from the adsorbent layer that remove and then generate to be the crystal. This is the first of 5 principles. And also we can express in terms of the secondary nucleation as is a function of Kn. That's right. It's a function of sigma. Kn is a constant. Sigma is the relative supersaturation. It's also the concentration. It depends on concentration. It depends on temperature. The omega is the internal speed, depends on mixing. Mt is the mass concentration or subtension density. It depends on amount of solid that subtend in the liquid. That's right. This is the mechanism or the parameter that affect for the nucleation based on secondary nucleation. It depends on concentration. Concentration means the concentration of solute dissolved in the solvent. Temperature, that's right. Like the mixing speed is density of the subtension. That's right. It's the parameter. Okay. How to measure the nucleation rate? There are many techniques that I will show you the technique that I use in my research. The first technique we call it directly observation. Directly observation. We use the microscope. That's right. We use the microscope. For this case, this is the solubility line. That's right. Solubility line. And this is the meta-stable zone. This is the meta-stable zone. That means only the growth in this zone. That's right. Above this nucleation. For this case, we would like to measure the nucleation rate. Okay. We start at point 0. As I talk to you, at point 0 is undersap. That's right. Point 0 is undersap. Okay, we prepare the solution at T0 at undersap. And then you reduce the temperature to this point, we call the T-sap. T2 being the T for growth. But for this case, we measure the nucleation. We have to reduce the temperature until it's the supersaturation zone, the higher supersat. At point 1, the crystal can be nucleated spontaneously or can nucleate by the solution itself. That's right. Okay, for this at point 1, what is the point 1? Okay, it times 0. T0 we reduce until with the T2 like this, and then T1. Okay, and this point we have some crystal nucleate, and then you reduce the temperature into the meta-stable zone quickly and hold at this temperature for about delta T1. Why we hold this? Because at the initial state, the crystal nucleate, but it's very, very small size. That's right. It's very small in size. we cannot detect by the microscope. Okay, after the crystal nucleate, you reduce the temperature or you increase the temperature. That's right. Again, when you reach 0.1, you increase the temperature back to 0.2. That's right. When it's reached 0.2, there is no nucleation. There is no nucleation. For this point, it's only growth of crystal. What does it mean? At this point, we hold about the time delta T1. That's right, at T1, at temperature 1. For this case, we would like to increase the size of crystal into the size that the microscope can be detected. That's right, can be detected. And then if the particle size of crystal size is larger enough, you can count the number of crystals. That's right, you can count the number of crystals by the microscope, something like this. This is the technique. That's right, we have 3 steps. We prepare the solution for undersat, and then you reduce the temperature to the higher supersaturation, is higher than metastable zone, and then the crystal nucleate. And then you increase the temperature rapidly to the zone of metastable zone for growth. That's right. Because at 0.1, the size of crystal is very small. We cannot detect it by the eye or by the microscope. That's right. At 0.2, the 0.2 we hold the temperature is for some time. That's right. To increase in size. When the size of crystal increase, you can detect the size, and then you can count number of crystals. Okay, this is the example of technique to determine the nucleation rate. This is the equipment that I use in my research. We have the microscope, right? And also, this is the picture from the microscope. You can count the number of crystals. That's right. Okay. And for this case, we plot the number of crystals. We plot the number of crystals. That's right. The number of crystals and time. That's right. Like this equation, and then we fit the number as a function of this equation, and then you differentiate this equation dn by dt. That's right, dn by dt, and then you can approach delta t approach 0. We can calculate the nucleation rate at the initial state. For this case, we have to determine at very initial. That's right, at the initial state. Okay, we can leave, and then you take delta t approach 0. When delta t approach 0, this term is equal to 1. You get dn by dt equal to AB. This is the nucleation rate. That's right, nucleation rate. Okay, this is the technique that I use to determine the nucleation rate. Nucleation rate, the unit is the number of crystal per volume of solution or per volume of magma and per time. That's right. This is the nucleation rate. And also we can show the nucleation rate as a function of concentration in terms of driving force. If you found that at lower temperature, nucleation rate is lower than higher temperature. That's right. At the same concentration, this is about 5 and 25. And sorry, this is 25 and 30. At 25 and 30, the nucleation is close together the same or similar. But at lower temperature is 18, it's lower than the higher temperature. This we can show the effect of the temperature and effect of concentration. At higher concentration, nucleation is higher. At higher temperature, nucleation is higher. And also this table, that's right. You can check the effect of interfacial energy. That's right, interfacial energy. At lower temperature, higher interfacial energy. That means lower nucleation rate. That's right. Lower temperature, higher interfacial energy, lower nucleation rate. This is correct. That's right, the common sense. At higher temperature, lower interfacial energy, higher nucleation rate. Okay, this result is correct based on the theory that we show in the classical nucleation theory that I talk to you later. This equation is support this theory. That's right, this theory. That's right. It's lower interfacial, higher nucleation rate. Its higher temperature is higher nucleation rate. And the result of that data is correspond to this theory. Okay. And also in my research, I used FBRM to detect the nucleation rate. So for this case, we have the equipment, the scatterite, and we have the computer to record the amount, to record the number of crystals. That's right. And to record the temperature online for that case. With this book, and we have the reactor control the temperature by water bath. We have the jacket. That's right. We use the magnetic sensor for mixing. This is the equipment that we use. And FBM also we measure the number of crystals. This is the number of crystals. That's right. The number of crystals increase with time. That's right. Increase with time. And also you can fit like the previous and fit the number with time. And then you determine the slope or determine the delta T approach zero. That's right. You get the nucleation rate. Right. This is the technique that we use in our lab. That's right. This is the nucleation rate. It's a function of temperature. And also it's a function of the ethanol or anti-solvent. For this case, we measure the nucleation rate of amino acid in water and in another solvent. We have three components: is water plus ethanol plus amino acid. That's right. For that case, we have the effect of ethanol to the solubility of amino acid in water or nucleation rate in water. Right. If we consider if we add higher in percent ethanol, you will get higher in nucleation rate. That's right, higher in nucleation rate. We call this the anti-solvent crystallization, because we start from the mixture of water and amino acid, and then we add ethanol. This ethanol will reduce the solubility of amino acid in water, and then it induce the nucleation, induce the crystallization. That's right. All of the data is the same trend. That's right. 10 Celsius, 25 Celsius, 40 Celsius. When you increase the percent of ethanol, you will increase in the nucleation rate. That's right. Okay. And also this is we report about the log J over S and log 1 over log S squared. We get the linear line. That's right, linear line for that case. And also we determine the interfacial energy. It's a function of temperature and a function of anti-solvent. Okay, the last kinetic, we have two kinetics. That's why we have the nucleation and growth. I talked to you. If we would like to control the size of the crystal, you have to operate in the metastable zone. In the metastable zone, it's only the crystal growth. That's right. It's difficult to induce the new crystal. That's right. Okay. If you would like to increase inside of crystal, you have to seed the crystal. We call this seed crystal. We have to prepare the crystal and then feed into the solution at the metastable zone. That's me, the metastable zone. We have two steps for this case. We call this the solute molecule. That's right. Solute molecule in solution. In solution, and then solute molecule diffuse into the surface of the crystal. This is the crystal. That's right. Surface of the crystal, and then integrated to the site. That's right. The preferred site. That's right. The preferred site. And then many solute diffuse, and then the site is full with the molecule of solute, and then the size of crystal is increased. For this case, we can control the size of the crystal. We have two steps: diffusion and surface integration. That's right. Diffusion and surface integration. The diffusion means solute in the solution diffuse to the surface of the crystal, and then this solute integrate into the site. That's right, into the site that is preferred. That's right. That is the mechanism of crystal growth. From smaller crystal size is bigger inside based on the growth of the crystal. Right, okay, also the growth G we represent by G. G is growth rate. Growth rate means the site change with time, dL by dt. That's right, dL by dt. We call it the linear growth rate. That's right. And sometimes you can correlate with the linear growth rate based on the mass. That's right, mass deposit rate or mass growth rate. We can count in terms of mass. You can measure in terms of mass of crystal. That's right. Okay, Rg is the mass deposit rate. Mean dmc by dt equal to 3 low kvl square dl by dt. Kv means the volumetric shape factor, volume shape factor. Is density of crystal. L is the characteristic length of the crystal. That's right. And you know, right, dl by dt is growth rate. And then you can correlate between linear growth rate and mass growth rate by 3 low kvl squared. You have to know the density of crystal. You have to know the shape factor based on volume. You can correlate between Ig and G. That's right, Ig and G. And also we know, right, L squared equal to AC divided by Ka. That's right. AC is area of the crystal or surface of the crystal. And then you can correlate the Ig equal to this term. Okay, you can correlate between mass growth rate and linear growth rate. Linear growth rate means dL by dt. The change in the design with respect to time. That's right. We call this is the delta L or delta L log. Okay. However, like many crystals are known to violate this law and exhibit site-dependent growth. But in generally, the growth of the crystal at different sites will be result in the same growth rate. But sometimes different site is different growth rate. Right? Different site is different growth rate. We call this is the growth dispersion. The growth dispersion. That's right. That the same site grow. It's some crystal. That's right. Growth dispersion means that the same site grow at different rate. Grow at different rate. That's right. Grow at different rate. So sometimes site dependent growth, different site grow different rate, and also the same site grow in different rate. We call it growth dispersion. That's right, growth dispersion. Did it give you some example of the growth rate of some molecule in bioproduct, like the amino acid? So this is amino acid. Right, this is the growth rate. This is the supersaturation at temperature. And this is the glycine, that's right, glycine. This is L-histidine beta form, something like this, lysozyme, this protein, this sucrose. Sucrose at different temperature, different concentration, and also different growth rate. The growth rate, the unit of growth rate is the length per time. That's right, because the growth rate is the change in the size with respect to time. That means the unit should be the length or distance per time. Less of growth. Okay, I'm sure before. And I talked to you, right? The growth rate is depend on the diffusion of solute to the surface of the crystal, and also the integration of the crystal on the surface, right, to the side. There are many theories that we describe the growth rate. The common theory is diffuse integration theory. Mean these two steps. That's right. The first step, the solute diffuse from the solution, right, to the crystal surface. And the second step, the solute on the crystal surface, insertion or displace or diffuse or integrate into the site. That's right, into the site. Sometimes we call it the reaction step. Like for this theory, we can express in terms of Ig as a function of delta C. That's right. As a function of the Kg. Kg is the overall growth rate coefficient. G is the growth rate order. And AC is the crystal surface area. We can express in terms of this equation for the diffusion integration theory. Right, from you know, right? This is the Ig. That's right. This is the Ig. You substitute Ig. You write Ig, and then you substitute Ig. Ig, and this is the diffusion equation. And then you can solve for G. That's right. G. G is equal to this equation. G is a function of the driving force. That's right. It's driving force. Driving force means the difference in concentration. And also we can group this term as the KGL. KGL is overall growth rate coefficient. Overall growth rate coefficient. As I talked to you, that's like for the growth, we use the growth to control the size. That means for the growth, we have to see crystal, see small crystal, add to the crystallizer. Like for example, we have the crystallizer, we have the mixer, we have the solution. Right. This solution should be metastable salt. And then we add the crystal. We add the crystal inside the crystallizer. And then the solution, that's right, the solute in solution will diffuse to the surface of crystal and indicate to the preferred size. And then the size is increased. You can control the size for that. That's right. Okay, to say. Like it for example of the growth is a function of concentration of glutamic acid. The function of concentration of glutamic acid. Okay, I will break for 10 minutes. That's right. Before we continue on